Hello, welcome to Maths with EJD. In this video, I'll be taking the graphical solution to a profit maximization problem, and the question is as displayed on the screen. So, a company specializes in the manufacturing of two products. So you can see two products to start with, and then the products are wristwatches and pocket watches. Okay. To produce each unit of either product, the company must allocate time on two machines. So you have machine one and machine two. Then each unit of a wristwatch contributes $3 to the company's profit, whereas each unit of a pocket watch contributes $5. Then the company faces constraints based on the available machine time. Machine one can operate for a maximum of 8 hours. So this is a constraint right there. Each unit of a wristwatch requires 1 hour of machine one's time, while each unit of a pocket watch demands 2 hours. Similarly, machine two has a maximum of availability of 12 hours. For this machine, each unit of a wristwatch requires 3 hours, and each unit of a pocket watch requires 2 hours. So it is essential to know that the company cannot produce negative quantities of either product. Therefore, the production levels of wristwatches and pocket watches must be zero or positive. Now, this, in fact, even if it was not told us, we already know that there must always be non-negativity constraints, whether that statement is there or not. Okay, so this is whether we are told or not, we need to know that there's always non-negativity constraints, except if the situation in the situation we are considering, negativity is allowed. So whether that part is there or not, we should always know that. So the company's task is to strategically determine the quantities of wristwatches and pocket watches to manufacture, ensuring that the product remains within the limits set by the machine availability, while simultaneously aiming for the highest possible profit. Okay, so that's the question. Now, in the previous video, I already explained uh, a smart approach to answering this kind of question. So, and the issue is, first of all, you need to decide your decision variables, right? So we can say so since we are dealing with wristwatches and pocket watches, so we can say let W, if you like, be number of wristwatches, number of wristwatches produced, okay? And then we can also let P be number of pocket watches produced. Okay. Now, once that is settled, then you can go through the question. The first part of the question says wristwatches. Okay, to produce each unit of either product, the company must allocate time on two machines. Okay, so we have machine one and machine two and all of that happening. So each unit of a wristwatch contributes $3 to company's profit. So now we can tabulate. We say wristwatches. Or okay, and we want to color code that. So we have wristwatches. Okay, wristwatches and pocket watches. Okay, so we can write it out this way so we can follow. Okay, I guess I'm going to need some space. Let me just say wrist watches. Okay, wrist watches and then pocket watches. So I can have some space left and right. Wrist watches, pocket watches. So something like this. So the first part says, okay, we have two machines, machine one and machine two. But before we get to the machine part, each unit of a wristwatch contributes $3 to the company's profit. Okay. So if you talk about profit now, we have wristwatches contributing, each unit contributing $3, while each unit of pocket watch contributes $5. So that's talking about profits now. And the next thing we have that the company faces constraint based on the available machine time. So machine one can operate for a maximum of 8 hours. So if we put like constraint here, okay, we put constraints here. So we have machine one. So machine one can operate for maximum of 8 hours. Then We also have machine 2. So for machine 2, it's okay, let's just follow. Each unit of it. Now, machine 1 can operate for maximum of 8 hours, but each unit of wristwatch requires 1 hour of machine time, while each unit of a pocket watch demands 2 hours. So for wristwatch, we need 1 hour on machine 1 and 2 hours on machine 2. Something like this. So it means that what everything you if you put everything together, it cannot exceed 8 hours, right? Now, then that is settled. Then for machine 2 now, um, okay. Similarly, machine 2 has a maximum availability of 12 hours. So machine 2 is only available for 12 hours. So that's a constraint right there. And once that is taken care of, each unit of a wristwatch requires 3 hours and each unit of a pocket watch requires 2 hours. So this 3 hours and this 2 hours again. Okay, let's look at that. Um, 1 hour, 2 hours, then 2 hours, then machine 2, wristwatch 3 hours, pocket watch 2 hours. Okay. What else do we have? I think that's about all we need, right? So in this case now, we can now go ahead and say that if each wristwatch contributes $3, so it means that if you produce W wristwatches, you are going to have 3 W dollars in profit. Then if you produce P pocket watches, you're going to have 5p dollars as profit, so that the total profit will be something like 3W plus 5p. Okay. Then talking about machine 1 now. So machine 1, each unit of wristwatch requires 1 hour on machine 1. So it means that if you produce W wristwatches, you are going to have a total of W hours on machine 1, while you're going to have 2p hours on machine 2, so that W plus 2p will be, in total will be less than 8, because you have a maximum of 8 hours. And when you talk about machine 2, this is machine 2. So when you talk about machine 2 now, if you produce W wristwatches, it means you're going to spend 3W hours on machine 2, and then you're going to spend 2p hours on machine 2 for pocket watches, so that you now have 3W plus 2p less than or equal to 12 hours, since you cannot spend more than that. And of course, uh, we automatically have this non-negativity constraints. So that simply means W and P will always be greater than or equal to 0. So overall now, we have we have the problem taken care of. So we can now say we want to maximize, or maximize Z equals 3W plus 5P, 3W plus 5P, and then that is subject to the constraints. So what are those constraints now? W plus 2P is less than or equal to 8. W plus 2P is less than or equal to 8. And then you have 3W plus 2P, 3W plus 2P is less than or equal to 12, while W and P are both positive. So with that, we have this problem taken care of. Okay. Now, since we want to use graphical method to solve this, right? Um, we can then go ahead to do that. All right. And to solve graphically, right? First of all, you can leave this out first and concentrate. So this is where you start with. Start with constraints. So you start with constraints. And what that means is that since you want to use the graphical method, you have so you can say your first line now, you can call that line 1 is going to be W plus 2P is equal to 8. So you forget about the less than or equal to, first of all. So W plus 2P is equal to 8. Now, if that is the case, then you can say that at P equals 0, right? When P is 0, that means that W will be 2. So you're going to have, so this expression now is going to be W plus 2 times 0 equals 8. That means that W plus 0 equals 8. And that means W is simply equal to 8. So in that case, you have a point, which is W is 8 and P is 0. So this point is, you're going to plot this point on the graph. Okay. So that's one part. The other part is this. So you can say that at W equals 0, when you set W to 0, right, that means you're going to have 0 plus 2p equals 8. That means you bring this down here. So 0, so if W is equal to 0, so you have 0 plus 2p equals 8. That means that 2p is equal to 8. So if you can divide both sides by 2, okay, so it means that p is equal to 4. So again, you have another point. Now W is 0. So W comes first. So you have 0, comma 4. So you have these 2 points to plot on a graph. Okay. So so you have to keep these points because you need to plot them on a graph later. So then you do the same thing for the second line you need. The second line is 3W plus 2P equals 12. So you can say L2 L2 is 3W plus 2P equals 12. So forget about the inequality first of all. So you have 3W plus 2P equals 12. So you can say that at W equals 0, okay? That means you have 3 times 0 plus 2p equals 12. That means 0 plus 2p equals 12. And then 2p equals 12. So that you now have 2p divided by 2 equals 12 divided by 2. So 2 cancels 2. And then p is equal to 6. That means that you have 0, comma 6. So that is w, comma p now. So that's 0, comma 6. Then you can do the same. So this is what you're bringing down here now. So you can do the same again. You say at P equals 0. So that means you have 3W. So you're bringing this down here. So you have 3W. You have 3, okay. You have 3W plus 2 into 0 equals 12. So this is what you've brought down here now. So that is 3W plus 2 times 0 cancels out. So that is basically, this cancels out and you have this is equal to 12. So 3W over equal to 12. So divide both sides by 3. This cancels out. So W is equal to 4. So that means that the other point you're going to have there is, P is 0 now. So that's 4, comma 0. The order is important. W comes first, P comes second. So now you have 4 points you're going to plot on the graph. So if there are more constraints, you can go on with all the L1, L2, L3. But now we have just 2 main constraints. The other constraint is non-positive, non-negativity constraint. Now with these points you have now, so let's list out the points. Uh, so we have, uh, so we have coordinates. Okay, what are the coordinates we have? The 8004. So 80 and 04 as the first we have. The second one is 0640. Okay. Okay, let me do it's either way, 0640. That's what we have. So these are the points we have. So the next thing you're going to do is try to plot a graph. So now this is like, so this is x-axis and this is your y-axis. So, or better still, following what we have, right? We have W is the x-axis, P is the y-axis. So we can do that. Then WP, 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 WP. So look at the biggest W is actually 8, as you can see, right? So you can say this is 2, 4, or maybe that's too small. So we can have 2, 4, 6, and 8. Or maybe we can even go to 10. Okay. So for W, the biggest W is 8. And the biggest P is actually the 6. So you can also go that way. So you have 2, 4, 6, 8. That way. Now, for L1 now, so this is for L1. That's the first line we need to plot. So this is 8, comma 0. So when P is 0, W is 8. That means it's along this line. So So this is 8, 0. W is 8, P is 0. That's along this axis. Then if you have 0, 4. 0, 4 is actually it will be this 4. And that is line 1. Okay. So since that is line 1, right? So you can join that. Okay. You can join that. Now, at this point, you have to, it's better you shade immediately what you need to shade. And for line 1, right, you discover that it is less than, so this inequality can come into play now. So less than or equal to. So line 1 is less than or equal to, very important. So less than or equal to means that you are shading the other side. You're shading up like this, you know. Oh, okay, sorry. Um, Okay, well, there are two. You can actually shade in two ways. You can shade the region you need, and you can shade the outside region, the other region, the region you don't need. So maybe, let me see, what style should we adopt? Okay, I think it's better to follow the less than or equal to. So less than or equal to simply means that if 4 is here, right? Less than or equal to 4 is everything below the line, but greater than or equal to is everything above. So it's more like if you shade down, you are going less than 4. If you shade there, you're going less than 8. So less than or equal to will be all this region like this. To be all this region down here this way. So that is less than or equal to 4. Everything here is less than or equal to 4. So that's the first line. Okay. Now, the second line, line 2, I think that's also less than or equal to based on the original thing. So less than or equal to is what we have for line 2 also, which is which has the corresponding component 0, 6, 4, 0. So again, I go 0, 6. That means when W is 0, P. Okay, normally this should actually come first to avoid confusion. So 4, 0, right? So when W is 4, P is 0. So that's this point. Then this one can come back. So 0, 6. So when P is 6, W is 0. That means this particular point. So again, we can so you can see these 2 points now. So you can connect those 2 points with a straight line. Okay. So you connect those 2 points with a straight line. And if you're talking about less than or equal to, so it means you're also shading below. Less than or equal to is below. Greater than or equal to will be above. So it is less than or equal to. Okay. Less than or equal to that way. So you shade that. Now, the the region of interest to you now is going to be any region where the shadings overlap, where both red and blue line overlap. And I think it is, of course, and that is also within the boundary of the lines. So that is looking like this region now. Okay. It's looking like this region. Right. So this is the region for it. So, I mean, with this now, we have what we need. So this is actually what you can call the feasible region. This is the feasible region. Okay. So, and it is very important to pay attention to the corners. Like, I guess if I if I would take another marker now, say take black. So these corners are really important, in looking for your solution. Okay. But because the graph can be confusing, so one thing we can do is, if you're using a graph sheet, I mean, maybe that can work better, right? But we actually have a surgical way, a precise way of dealing with that. So we want to see all the points. So if we solve these two simultaneously, like if we solve this and these two equations simultaneously, we can get precise locations where the lines intersect. So, okay, so we can say solving L1 and L2 simultaneously. Okay, we want to solve them simultaneously. L1, you remember, is W plus 2P equals 8. Okay. W plus 2P equals 8. And L2 is 3W plus 2P equals 12. Okay. Um, yep. So if you solve this simultaneously, you can call this equation 1 and call this equation 2, for instance. But interestingly, you can already see that 2P and 2P are the same. So we have a very easy way to go. Have a very easy way to go. And in that case now, so we can just say equation 2 minus equation 1, because these two are the same, so they'll cancel out. So 3W minus W, you have 3W minus W, right? 3W minus W plus 2P minus 2P. So that is this minus this, and that is equal to 12 minus 8. So this simply cancels out. So 3W minus W is 2W. 12 minus 8 is 4. Yeah? 12 minus 8 is 4. So it means 2W divided by 2 is equal to 4 divided by 2. So W is equal to 2. Okay? So you get W equals 2. Then, what else do you want? We also, so we have that, right? And then uh we can now solve for P. So we can say from from any of the equations, from W plus 2P equals 8. So we can have W is 8 now, so we have 2 equals 2P equals 8. So 2P is equal to 8 minus 2. So 2P is equal to 6. So that P is 2P over 2 is 6 over 2. So this cancels out. So P is equal to 3. So here now we have, so we can say therefore, um, we have W to be 2. W is equal to 2 and P is equal to 3. Now, the issue is we now need to find out if this is actually the optimal solution we can get in this situation. Okay. Um, So in this case now, I mean, these are just the two things we have. So that is 2 comma 3. And it will interest you to know that this, I mean, my graph is not perfect, right? So this is actually that point, 2 comma 3. So this is 2 comma 3. But it's not looking perfect. So this is the point 2 comma 3. And since we don't have any other solutions, we don't have any other solution. So that will automatically have to coincide with our optimal solution. Of course, the other options you can consider is this corner, okay? This corner, uh, that is, we have 0, 0, and this is like uh 4, 0. Okay, maybe I should do that. Let me use black now. This is 0, 0, the four corners. Then this is 4, 0, right? Then this is 2, 3 that we just found, and this is 0, 4. Okay, so these are possible optimal solutions you can have. So we don't know which is which now. So these four corners, having identified them, so these four corners are most likely going to be our optimal solutions. So we can say that. But I mean, what this thing we just solved now actually gives us it's so reading it from a graph, right? We could have just done this without even solving that equation. But solving the equation gives you a bit more confidence in what you are doing. So we can say possible, possible, possible. Okay, we can say possible solutions. Possible solutions are uh okay. Maybe we may, in fact, we may not have to, we may not even worry ourselves with with 0, 0, because normally you already know that's not going to make any sense. So we have 0, 4, 2, 3, 4, 0. So possible solutions are 0, 4, 2, 3, 4, 0. So how do you know which is which? So these are possible solutions now. So how do you know which is which? So you go to Z. Let's say this is point. This is how did I write that? 0, 4, 2, 3, 4, 0. Okay. So let's say this is point A, this is point B, and this is point C. Okay. Then you go back to the objective function Z. So the objective function Z is 3W plus 5P. This is now where you come to that. 3W plus 5P. That is the objective function. So you have 3W plus 5P. That's your objective function. So for you to know which of the solutions are optimal based on what you have identified from the graph now, these 3 points. So these 3 corners, if you look at the overview I gave previously, so the 3 corners are most likely going to be one of the give you the, so these are possible solutions, but the optimal one is what we want now. So this is A, this is B, and this is C. So that if we now have ZA, that will be ZA will be 3WA plus 5P. So now this is WA, this is of plus 5PA, right? WAPA, WB, WB, PB, then this is WC, PC. Okay. So this is simply just going to be 3 times 0 plus 5 times 4. And that is easily, but we can bring that down. This is 0 plus 20. So 20 is what you get if we check this out like that, then so for ZB now, for ZB, we have 3WB plus 5PB. Okay, that is 3. WB is 2. 5 times 3. Okay, that is this now. So that means 3 times 2 is 6, 5 times 3 is 15, and you get 21. And lastly, you have ZC, which is 3WC plus 5PC. So that is 3 into, so this is now 40. So 3 into 4 plus 5 into 0. So that is 3 times 4 is 12, 5 times 0 is 0. So that is 12. So if you look at all of this now, so which one is maximum? So optimal solution, which you can call Z star if you like, would actually be the maximum, to be the maximum of ZA, ZB, and ZC. Okay, so that means which is the biggest of ZA is 20. So you have 20, 21, and 12. So the maximum, of course, is simply 21. Okay, so you can now say, therefore, the optimal solution, the optimal solution is W equals 3, right? W equals 3. Yeah, sorry, W equals 2. W equals 2. W equals 2. P equals 3. And the maximum profit and the maximum profit is Z equals 21. So now you can just say, now based on your recommendation, now based on what you have done, you can say, therefore, the company can make a maximum profit, can make a maximum profit of $21 by producing two wristwatches, by producing wristwatches, two wristwatches, and 3 pocket watches. Okay. So so if you're advising this company now, this is a very logical and scientific way of recommending to them how they should be producing, right? So with this, I come to the end of this particular video. So just go through it, try as many questions as possible, and you'll see that it's not, it's something that you can easily deal with. Okay, for you to get the graph right, it's better you use a scaled graph so that you can get actual values. Then, of course, if you are you can use a graphing calculator like Desmos to plot the points, and then you can see how these things go. I'm also going to use Python to do this so you can see what that looks like. So you can try out Desmos to plot the lines and see. There you can get maybe I should even demonstrate Desmos right now. Let me see if I can do that. Let me demonstrate with Desmos. It makes things really easy. Just to so if you want to be very accurate, Desmos can be helpful. So it's a graphing calculator. So all you just need to do with Desmos is this. So you look at your constraint. W plus 2p equals 8. 3w plus 2p is okay. I mean, you are going to use the inequality this time. So you have, but you can't use w here. So you can say 2x, sorry, 2x, rather, w plus 2p is like x plus 2y, x plus 2y is less than or equal to 8. Now you can see it as shaded. Can you see just like what the shading I did the other time? W plus 2y is less than or equal to 8. Then the other one is now going to be 3x. That's like 3w plus 2p is also less than or, I mean, not p now, y. So you can use xy is less than or equal to 12. So you can see it has carved out that region for you so that what you now need, you need that region. So you see the 3 points I did before, so you can see how this goes now. So where the green and blue overlap, that is where your focus is going to be. And it is somewhere around here. So you can see where blue and green overlap. So you can see this is your, if you point at it, that's 0.4. This is 2.3. And this is 4.0. Okay. This is 4.0 like that. Of course, this is the origin. This is the origin now. So those are the 4 points I used now. This 0.4, 2.3, and this I mean 0.4, 2.3, and 4.0. So you can see this is the region you are interested in. This is the region you are interested in. So from there now, so with these 4 points, you can now substitute into the graph like I did the other time, and you can get your result. So with this, we come to the end of this video. If you have not subscribed to this channel, you can see already that you have a whole lot to learn and you don't want to sleep on it, like they say. So get subscribed and hit the notification bell so you can always get alerted when a new video is released. And don't forget to comment. Tell me if you want me to teach a topic or if you want me to solve a problem, and like also and share with as many people as possible so they can be part of all this great learning. In the next video, I'll be showing you how to use uh, a Python code to deal with this kind of problem. So look out for it. It's going to be interesting. So because I mean, when the problem gets more complicated, you need some kind of programming to get it settled. So till that time, have a great see you. Keep trying, keep optimizing. Bye.